Okay, now that the exam is all behind us and we're not worried about it anymore, we're going to continue with our discussion on regression. It will not be a very long lecture today. I think we can head out a little earlier. But I just want to wrap up this discussion on standard error, standard deviation, the R-squared value, etc., and just gonna pin that in your brains forever and ever and ever. Okay. Last time we left off at this point where I was asking you to do this activity where, if you remember, we had defined the standard deviation. And the interesting thing we did with the standard deviation was say, treat the standard deviation as the error committed by using the mean value to represent all your data. So if you had a bunch of data and you're just using the mean value to do a prediction on those data, then the standard deviation is the error committed by using the mean value to model your data. Now, contrast that to the standard error when we are using a regression curve. In this case, we were just doing a straight line. We're going to extend this to any curve later. But that standard error was the equivalent of the standard deviation with the mean value. Is just how far are the data spread around your regression line. And you can take the formulas for the standard deviation, standard error, and compare them. It is simpler to compare the total error committed when using the mean value versus the total error committed when using regression. So SR refers to regression, ST refers to Tony. I don't know what it refers to. ST is just the one using the mean value, okay? And then I asked you last time, this difference means something. And you had two cases. If the error committed in regression is comparable to the error committed using the mean value, and if the error committed in regression was less or much less than the error committed using the mean value to describe the data. And we concluded last time that this difference, so we said that if SR and ST are comparable, in other words, if the error after you do regression is about the same as the standard deviation or the error when using the mean value, then you haven't improved on using the mean value as a model for. So regression, no good, is bad, okay? Didn't do anything, didn't improve over using the mean value. Whereas if your error after regression is smaller than your error prior to regression with respect to the mean, remember, we always treat the mean as our gold standard reference, then you have improved on using the mean value as a model for your data, okay? The other case doesn't exist when SR is greater than ST, because by definition, regression, the worst case is going to give you like the mean, something comparable to the mean value. It's supposed to improve your model of the data. So that difference technically quantifies the improvement. If you take the difference between these two, it quantifies the improvement that the regression has made over just using a mean value to describe the data. So if this difference is 0, then you've done no improvement, okay? If this difference, on the other hand, is very large in absolute value, then you would have done a tremendous improvement. And that's what we're headed. We're headed to quantify how well the regression is behaving, okay? So to simplify this calculation, we simply normalize by the error committed using the mean value so that we get something between 0 and 1, okay? And we define a quantity called the R-squared value, or the coefficient of determination. It's simply the difference between error prior to regression and error after regression, normalized by the error prior to regression. This quantity is always between 0 and 1, okay? So now we can say when R-squared is equal to 0, or close to 0, then you have a bad fit. In other words, ST and SR are comparable. You have not improved over using the mean value as a model for your data, okay? However, if SR is much larger than ST, much smaller than ST, sorry, then your R-squared value approaches 1, because you've reduced your error significantly. Okay, so you can look at it either on this formula or this formula. If SR is much smaller than ST, then this ratio is almost is very close to 0 or much smaller than 1, and your R squared value gives you 1. So if you've used the R squared value before and you've memorized that R square 0 is bad, R square 1 is good, R square in the middle is like, yeah, you know, is okay, then this is where this comes from if you haven't done the derivation yet. And I hope this helps you kind of solidify this idea of what it means to do regression. Okay, so we'll do a couple of examples here. Take these data, okay, and these data have the following average value. Okay, now just looking at those data without doing any calculation, go ahead and in your mind draw a regression line and tell me if SR is equal to ST or much smaller than ST, and then estimate the R squared value, whether it's close to 0 or close to 1. Okay, no need to do any calculations. Okay, so first draw a regression line in your mind. Where would it fall? Okay, yes, that's true. What does that mean? Yeah. Are you drawing it in your mind? You got. I can see a lot of kind of clouds popping from your heads with like lines all over the place. Okay, so let's see. Oh, put your name tag. Sorry, do you want to take this? Since you have an answer. So first, where do you think the regression line lies? Kevin? Yeah, just almost right on top of the mean value. Okay, so looking at those data, you know, the regression line is going to kind of be in between them, trying to minimize the error between them, and it's probably going to fall almost on top of the mean value. Now, what does that mean in terms of SR and